Assalamualaikum everyone. I'm Zunaira Qureshi, and the topic of today's presentation is unveiling the realm of smart biomaterials in health tech. These are the contents that I'll be covering in today's presentation. And I would like to start the presentation with a video to give you an idea of the smart biomaterials.
This could be the long-lasting, eco-friendly battery of the future. These small foldable battery cells are powered by moisture from the air. Put simply, the charge comes from keeping one part of the fabric wet by absorbing ambient moisture from the air and the other part dry. The difference between the wet and dry parts of the fabric is what creates a current. As the basis for the battery, we use this simple non-woven fabric made from wood pulp and polyester. First, we soak it in carbon ink. Then, we bake it in the oven. And finally, we apply a layer of hydrogel to one part of the fabric. A key component is this hydrogel. It is based on common sea salt, which, like the rest of the device, is cheap and easy to produce. A special property of the gel is that it absorbs up to 4.5 times its own weight in water. Inside this 3D printed AA battery case, we have 3 separate layers of MEG cells. This way, the battery generates a total output of about 1.5 to 1.9 volts, the same as a regular battery. That is enough to power something like this alarm clock.
We have tested the device for several weeks, and it continues to output the same charge. We believe it can last as long as there is moisture in the air.
So we have also developed moisture-enabled electricity generator in our lab, and it generates a voltage of 2.3 volts at 25% humidity and 25 degrees Celsius at room temperature for continuous 10 days. I'll be discussing this in the later slides. So starting with introduction. Biomaterials are any materials of natural or synthetic origin that comes in contact with tissue, blood, or biological tissues. They are intended for use in prosthetics, diagnostics, therapeutics, or for storage application, and they do not adversely affect living organisms and their components. So, what are smart biomaterials? Smart biomaterials are any materials that are implanted inside human body, and the level of smartness has evolved in the past decades from inert biomaterials to autonomous biomaterials. So inert biomaterials are simple biomaterials that are biocompatible and they are implanted within the body and they do not have any interaction with the body. So in the next phase, active biomaterials were developed. These biomaterials they release drug into their surroundings. This can be drug or any tissue engineering, any signals for tissue engineering. In the next phase, responsive biomaterials were developed. Responsive biomaterials are actually the intelligent biomaterials, and they not only release the payload to their environment, but they also they do it in after sensing the cue from the environment. And this can be the cue can be pH, temperature, or anything. And in response to that, a stimulus, they release the drug. Today we are in the autonomous phase in which these biomaterials, they not only sense, they adapt, they respond and then adapt according to the changes in the environment, and then the cycle continues. So these are the inert biomaterials have minimal or no interaction with their environment. They were developed to avoid any toxicity or rejection from the human body. And the example include dental and hip implants, stents, contact lenses, heart valves, etc. The active biomaterials are the second level of smartness, and they have active interaction with the environment. They send one-way signal, which can be a drug or signaling molecule, and active biomaterials can be developed by loading biomolecules in them, and to develop drug delivery systems or systems for signaling molecules, for releasing signaling molecules. Active biomaterials can also be developed by engineering the surface or bulk properties of the material to enhance the adhesion or proliferation, to improve the surface. They can be developed as surface coatings, and they can be also developed as scaffolds. Um, Active biomaterials in the drug delivery systems, active biomaterials have revolutionized the therapeutics, as previously we had conventional drug delivery systems which were known for their poor biodistribution and several side effects. With the help of active biomaterials, we have different drug delivery routes today. These include transdermal, pulmonary, nasal, or any. We can also deliver the drug to the brain. So this is how far we have gotten into drug delivery systems, and these can be done through a variety of drug delivery particles, which include nanogels, microgels, solid lipid nanoparticles, carbon nanotubes, liposomes, etc. We can also develop drug delivery systems which may deliver drug ranging from 1 day to 200 days. So we can develop drug delivery systems that can deliver drug for 1 day, for 20 days, for 30 days, for as long as till 200 days. So the third level of smartness include responsive biomaterials. These are actually the intelligent biomaterials that are being used today, and they sense the stimulus from the environment and then respond accordingly by releasing the payload they have inside them. And they may respond. They may be redox responsive, thermoresponsive, light responsive, magnetic responsive, ultrasound responsive, electric responsive, pH responsive, and enzyme responsive. I'll be briefing about them one by one in the next slides. The fourth level of smartness is the autonomous biomaterials. In the autonomous biomaterials, the main concept actually is that we are using two different types of responsive biomaterials. For example, we use pH responsive material and redox responsive material, which can release the drug or the payload according to the stimulus. Once they sense a specific stimulus, and then accordingly they adapt, and then the cycle continues. They sense again and then respond, then adapt. This is how the cycle continues. These today we are in this age, and there are a very few biomaterials that we have today in this domain. So now I'll be showing the smart biomaterials that have been developed by our research group. Starting with the inert biomaterials, we have developed bare metal stents made up of stainless steel and cobalt chromium. We have also developed bileaflet mechanical mitral heart valve from graphite material. Recently, we have developed intracranial stent system, which includes the stent and the catheter. And these are a very few companies in the worldwide uh, develop these kinds of balloon expandable stents. And we are, I guess, the second company who has developed these stents. In the next, active biomaterials, we have developed anti-diabetic drug. We have also developed coronary drug-eluting stents, rapid pain relieving emulsion. We are right now developing drug-loaded embolic microspheres. So the anti-diabetic drug that we developed uh, is basically a polyherbal drug formulation, and it increases the insulin secretion and sensitivity by different mechanism of actions. And these drug was developed by using active biomaterials, which holds and releases the drug in 2 hours. In the rapid pain relieving emulsion, we develop. This is also a novel formulation that we developed for ameliorating the musculoskeletal and arthritis pain, and it is two times. It offers 2 times more rapid pain relief when compared with a commercial balm, and according to volunteers' feedback, it results in very much improved pain relief for arthritis, strains, and tendinitis pain. And while developing this formulation, we used active biomaterials. This is the product that we are currently developing. It is drug-loaded embolic microgel. Uh, in the market, these kind of embolic microgels are used to uh, embolize the blood vessels that are supplying blood to the tumor. So we are right now developing these for our novel application, and which we I cannot disclose right now, but it is going to be a game changer. So our group has also developed functional scaffolds for bone regeneration. These were developed using electrospinning and were made from PVA. In the responsive biomaterials, we have developed pH responsive gels, we have developed thermoresponsive gels and humidity responsive gels. Um, in the from the pH responsive gel, we have developed this device for smart wound management. So what this device does is it senses the wound pH and corresponds it to the wound health. Initially, in the wound stages, when the wound is fresh, the pH of the wound is alkaline, and when it heals, it goes towards the acidic pH. So this a module was developed so as to release the drug according to the wound health, and it uses pH responsive hydrogel, and it was licensed to pharmatech industry. So we have temperature responsive hydrogels, which we developed in our lab. There too, we developed NIPEM TECDA temperature responsive hydrogels, and we also developed chitosan gelatin temperature responsive hydrogels. These hydrogels, temperature responsive hydrogels, can be used as drug delivery systems for cancer, because the cancer cells have high temperature or ranging from 43 to 45 degrees Celsius, while the normal cells have temperature in the range of 37 degrees. So these temperature responsive hydrogels can be used to target the drug to the cancer cells only, so that we have minimal side effects or no side effects to the other cells. In the humidity responsive, using the humidity responsive hydrogels, we have developed this moisture driven electricity generator, and it was developed by using a very simple method of solvent casting, and its thickness is 50 microns, and the voltage that it generates is 2.13, and it generates 7.88 microamperes of current. And it can be seen here that with at 25 to 30% relative humidity, it is generating a voltage of 2.13 volts, and which increases by increasing the relative humidity. And similarly, if we see the relation with the temperature, then by increasing the temperature, the voltage is increasing. So we also have developed auxetic biomaterials. These are the materials which possess unique microarchitecture. So auxetic structures are actually they have negative Poisson's ratio, which means that if we normally when we stretch any material in one direction, it compresses in the other direction. So, but it is opposite with these materials. In these materials, when we them in one direction, they also expand in the other direction. So this makes them unique, and they can be used in for developing stents. So to avoid the stent migration, they can also be used for bone implants to reduce the stress shielding effect, which is very common with bone implants. So, in our group actually developed an intermedullary balloon catheter stent for tubular fracture. So the main concept is that the stent that we develop is implanted inside the bone in the intramedullary region by by making a small incision on this side.